Hello. Oh, Piotr. Hi.
Hi, Yoshi. How are you doing?
Fine, fine. Very good. Did you go to conference last week?
No,
Bedrevo? Oh,
no,
I see,
no,
I see.
no.
Uh-huh. Mihao went there, I think. Uh-huh.
I don't travel much this semester.
Oh, I see, I understand. Yeah, I have a problem to get into the to share the screen. So I should ask organizer how to share the screen.
I see.
Yeah. We have to schedule our meeting, Piotr, right?
Yes. We have to resume. But I'm resuming all the meetings, and let's exchange messages about it. About when you prefer.
Yeah. Good. This is a live streaming service, so if you talk, this is everyone listen. Good. Okay, so just a second. I should ask organizer. Hello, Professor Akagi. I cannot share the screen. I cannot share the screen. Some reason. Still, I have a problem. The file, the screen is visible? 見えますか? Screen is visible? Is the
すみません、
screen
比嘉先生、すみません、マイクがオフになってますね。聞こえますか？
マイクオフ。
あ、聞こえますか？僕の方がマイクオフになってました。
いや、聞こえます。I can hear you.
はい、ありがとうございます。ギガ先生の声も会場に聞こえてます。
聞こえますか？ OK。画面見えますか？
はい、画面見えます。
はい、
画面見えます。
はい。フルスクリーン。
And everything's okay. So, so it's basically divided into two parts. So maybe it's always.
Do you hear me? Mihao?
Yes, we can hear you.
Okay. Okay.
Okay, so before announcing the next couple of talks, which is the main lecture by Professor Yoshikatsu Giga, I just have a quick announcement for the people who are here, and please spread the word.
Sorry, I don't know if that's only my problem and if you can hear me, but I cannot hear anything.
I can hear you. I can hear you.
Headphones should work, but I don't hear anything.
You don't hear me?
We can hear you. We can hear both of you.
But some audience, Zoom audience cannot hear me. I don't know why.
I can hear you even via Zoom. So maybe his computer may have some trouble, I would say.
So
Okay.
let me make the announcement just for the lunch. I mean, there is a possibility in the campus to have several ways of having lunch. There is one that we can reserve for you, which is just right here in front. The price is €13. You will have to pay it yourself and you will get reimbursed the speakers with the per diem. And it will pass, I will pass a list. You just put a line, Mara is there with the translation in English. You just put a bar for one choice is for the first dish and one choice is for the second dish. We need to know the number of people because we have to tell them in 1 hour. Sorry for this technical message. And then, of course, there are other possibilities. So feel free to go in other places, and I will be happy to tell you, or you can ask the locals to tell you what are the other possibilities. So now I would like to resume the session, and it's a great honor for us to have here Professor Yoshikatsu Giga. He will give one long lecture, which will be split in two. First part, pause for 5-10 minutes, and then second part. And it will speak about the fractional time differential equation as a singular limit of the Kobayashi-Warren-Carter system. Please, Professor Gina.
Thank you very much for your kind introduction, and thank you very much for your invitation. I'm sorry I cannot come in person this meeting. Okay, today's the title of the talk is this one, but the talk consists of two parts. It doesn't work. Okay, the plan, here's the plan of my talks. The first part I describe stationary problems. The second part I describe non-stationary problems. And the paper is two papers here and one paper here. And the course are slightly different, but most of them are a couple of people, most of them are either my former postdoc or former student. Yeah. So let's go back. Let's get into the part one. This is joint work with Okamoto, my former student, Sakakibara, the former postdoc, and Uesaka is neither student nor a postdoc, but he was a Arisma company, and there's a joint project with Arisma, so that's the reason he's here. Okay. And the contents of part one is the following. First, we describe motivation, and then I discuss one-dimensional problem and the higher dimensional problem. And if time permits, I give you idea of the proofs. Okay, what is the motivation? Motivation is coming from multi-grain problem. And this is separated by phase boundary. So there are three phases, 1, 2, 3, and bounded by phase boundary. And the interfacial energy is of the typical interfacial energy is the length of each grain, but weighted by surface tension. This is typical interfacial energy, and of course this has a positive constant, and motion of gamma is a gradient probe E gamma. So this is a grain boundary is this part, and this is a it's a great. The motion of gamma is a grain boundary motion, and gamma ij, this part is expected to move with a mean curvature flow with weight and mobility. The kappa is a mean curvature. And in the angle, we use a Herring angular condition at triple junction. This is typical multi-grain problem. But what we discussed today is slightly different. Assumes that each phase has some structural constant, like average angle, U1, U2, U3, and assume that this sigma ij depends on Ui and Uj. What happens? And actually this model is recently studied by Epstein and Liu and Mizuno quite a few years ago, and this is a planar case. And that earlier study by Kobayashi and Warren-Carter, and this is a phase field approach, but no motion is expected for grain boundary. So grain boundary is standing, but the angle difference is changing. Yes. So what is the Kobayashi-Warren-Carter energy? Kobayashi-Warren-Carter energy is essentially total variation with weight. This alpha or 0v is a typical weight. V is typically choice is V square, and E epsilon SMM is in some sense single well modica motora energy. So this is a relaxation term, gradient V square, and this is a potential part. And typically the potential is just one well. So this one, yes. And physically speaking, what does it mean, this U and V? What is physically speaking? V is in some sense order parameter, and it could be it is if epsilon is small, V would like to be 1, and in this case, crystal structure exists. And when U is U indicates, for example, average angle. we discuss. Right. So it's a total variation. So the difference of average angle would like to make smaller and smaller because of this energy, but it may have a very, very big jump if alpha 0 V is very close to 0. So this is the part is often we call amorphous part. But anyhow, this is if alpha 0, if V is close to 0, then if alpha 0 V is close to 0, jump may be big, can be big. Okay, so the problem is what is the limit energy as epsilon to 0? So this is a typical something like gamma convergence problem. But conventional L1 topology is too weak for the singular modica monotoral type energy. So, okay, and actually Kobayashi, Warren, Carter consider the gradient form, okay, of this form. If you take a gradient, L2 gradient, you get such kind of form, but although there's some weight. In the part 2, we discussed this equation more carefully, but in part 1, we just mentioned this is the gradient flow. And note that this energy is looks convex, but it's convex for each variable, u and v, but in the combined, it's not convex because we have a term like v square mod gradient u. So this is no longer convex. But each fixed v and v, u and v, it's convex. So its well-posedness. So also this weight depends upon solution. So its well-posedness is still open problem since Kobayashi and Warren and Carter proposed 2000. Oh, this is wrong. I think 2002 or something. Not 22.0. 02 something. Okay, and there's a lot of study by Shirakawa and other people, and what they say is if there is something addition this term, and if there is some addition, either Laplace term is added or this term is added, then the global existence of solution known by these people. But if you talk about uniqueness, it's only known whether nu is positive in only one-dimensional case. There are many studies, but so far, original form, the well-posedness original form is not yet established. Even yes. Okay, the main topic today is the part 1 is this one-dimensional problem. And we consider this single, this energy, E epsilon. This is a Dirichlet part plus potential part. And the Dirichlet energy part is weighted by, multiplied by small epsilon. And this is a small epsilon here, the divisor. And so this is often called relaxation time from comparison here. And which this is well studied. If f of v is v square minus y square, this is called double well potential. While what we are interested in today is a single well type, this type. Okay. So the question is, does the minimizer converge to the minimizer of some limit energy, and what is the limit energy? So this is a question. And as I think many of audience knows this notion of gamma convergence, but let me quickly review the definition of the gamma convergence. If consider E epsilon and E, the sequence of energy combines the E in the sense of gamma. If there is a V for any, so this is the lower semi-continuity property, for any sequence combines V, we get such kind of lower semi-continuity. And this is for any V, there's a recovery sequence, W epsilon, so that this value is actually attained. So the only first inequality is not so interesting because E can be a very small energy. But if you add such second condition to find recovery, recovery sequence must exist, then this is much reasonable. And of course, these concepts, this English error, this concept concept depends on the choice of topology for V epsilon tends to V and W epsilon tends to V, of course. And as many people know, the merit of gamma convergence is if U epsilon is the minimizer of E epsilon, then the limit is a minimizer of E provided that U epsilon converges to U. One often needs to check the compactness to prove U epsilon to U or some U. But anyhow, this is the existence of minimizer for U epsilon essentially guarantees the existence of minimizer in the limit energy. This is good. So in the case of double well potential, this project is very successful. For example, if U epsilon under some volume constraint converges to such energy E in the L1 limit. So C is in one dimension, EU is a number of jumps, and U is just two value function, -1 and 1, and the average of course 0. Otherwise, this is infinity. And C is a computable constant coming from F. And this is rigorously proved by Modica and Mortora, and also in one-dimensional case, and the several dimension case, Modica and Peter Stamberg later, including higher dimension. This is well studied. So what is a typical problem for single well case? So consider the such interval -1 to 1, and consider the energy E epsilon B. This is E epsilon V plus B V0 square. So this is the value of 0 with positive B. What is the limit as epsilon tends to 0? L1 convergence, as you expected, it's 2 coarse. Because from L1 sense, this part is invisible. So what's the minimizer? Okay, you can skip this page, but W epsilon is a minimizer of E epsilon B with for H1 among H1 function. And fortunately, this can be calculated if FV of V minus 1 squared because the Euler-Lagrange equation, the linear equation. Right. Then we can, everything is explicit, and you can explicitly calculate the value of 0. The limit of value at 0. This is equal to 1 plus 1 over 1 plus B, and the energy W epsilon of energy epsilon E epsilon B energy of W epsilon combines to B over 1 plus B, and this is strictly big smaller than B. And this value is equal to, of course, if everything is 1, this is exact. The energy of constant function 1 equals B. This is actually smaller than this one. And I think it's better to see this picture. And this is just a small calculation of this linear solution of linear equation. And the red line, the epsilon is 0.1, and 0.01 is here, and if 0.001 is already something like that. So you see W epsilon converges to 1 almost everywhere, but we have to extract the finer structure of the limit, because if you look at everything just L1 topology, this part is missing, completely missing. Okay. So our problem is, what is the suitable topology to catch the above limit? And is it possible to prove the gamma converges under such a limit? So this is our problem. Okay, here's a related topic. Many people may be familiar. There's an energy called Ambrosio-Tortorelli functional proposed by 1989. And this energy is a function of U and V, and this is V square and gradient U square. This is a Dirichlet energy weighted V square and U minus G square. This is a fidelity term, but we have U E epsilon. That this is a single well Modica Mortora type energy. And in this case, if epsilon 0 gamma limit is a Mumford-Schech type functional, and this is this Mumford-Schech functional is of the form, and sigma is constant. And this direction energy outside K compact set, and this is energy. N-1 dimensional area, and alpha is a computable constant, and this term still remains. Okay, this our problem looks like very similar. Okay, this energy is has a lot of application. For example, to study brittle fracture, started by Frankfurt and Marigo, and also Steiner problem. For example, the work of Remnant and Santa Ambrosia. So there are many applications for this Ambrosio-Tortorelli type function. And okay, our model is what the difference from Ambrosio-Tortorelli energy is our part, our gradient part of U is a total variation, not Dirichlet energy. This is the main difference of from Ambrosio-Tortorelli energy. And in some sense, this is Ambrosio-Tortorelli inhomogenization of the total variation. So without this term, this is just a total variation. But if you V square, it's weighted, and this is becoming total variation becomes inhomogeneous. Okay. And the original E epsilon is considered as Ambrosio-Tortorelli inhomogenization of the Dirichlet energy, while this is the inhomogenization of total variation. So we can interpret this energy as a Ambrosio-Tortorelli type inhomogenization of the total variation. So what's the difference? In the case of Ambrosio-Tortorelli, the limit of V epsilon has the same depth, which implies that the set K is finite set for one-dimensional case. In our case, the depth of the limit is not the same. It depends on the size of the jump of U. So the set can be a countable infinite set, even in our one-dimensional case. So this is the main difference. So what is the relation between Kobayashi and Kata energy to our E beta? Yes. Yes, this E epsilon beta. Yes. Okay, if Ux is just a two-value function, use and it jump, then this is just E epsilon sigma V. Right. So this is in this trivial case, Kobayashi and Kata energy reduced to just a single well modica Mortora type with sigma V0 square. So what is the gamma limit under the graph convergence? Actually, we have to take graph convergence to see the limit. Okay, let's think about periodic case for simplicity. And let gamma be a set value function on M. So gamma is set value function. And the set B, calligraphic B, is a gamma, a graph of gamma is the all set value function on M, whose graph is compact in this M cross R spaces. So this is a bounded upper semi-continuous set value functions. Okay. And we say that gamma J combines to gamma under the graph convergence, shortly gamma J combines to gamma in graph. If the Hausdorff distance of gamma graph gamma J and graph gamma tends to 0. And if gamma Jx is the graph of single usual function, gamma Jx is a singleton, in this case, we simply write Gj tends to gamma. And for the detailed analysis of set value functions, there's a very nice book by Oban and Franz Koba. The title is Set Value Analysis. This is very nice. So what is a modica Mortora function? We consider such kind of modica Mortora functional plus BVA square. So this is our energy, our energy. And F is just FV is equal to 0. a single minima. And of course, in the infinity, if V tends to infinity, this is non-degenerate, and we consider V is the square root of f of tau d tau, integrate from 1 to V. And then this is actually limit energy. Limit energy, or limit modica Mortora energy is 2 times of gamma xi minus and xi I plus. And I shall explain this notation with sigma xi is in the set A0, otherwise infinity. And this single modica Mortora type energy, limit singular modica Mortora is the size is E0B. This is actually E0 SMM plus this B times minima of xi of A at the plus part. A is a given, by the way, A is a given point. F plus denotes positive part. So I'll explain more. What is this? Okay, so it's better to explain the main result of this paper. Let V epsilon is only have H1. And suppose that it's a solar space. Suppose that V epsilon tends to xi in the graph sense. And it's a good graph. And then E0 B SMM. Xi is in some sense this convergence lower semi-continuous, even for epsilon, so inf of E epsilon B at V epsilon is always greater or equal to this is dominated by the limit one. In particular, this xi belongs to A0. What is A0? A0 is a following. Xi is belongs to a bounded lower. Xi is bounded lower semi-continuous set valued function, right? And xi x equal to 1 except countable number of xi, and xi at xi. Xi xi is equal to xi I minus and xi I plus. This is of course containing 1. So if of course the case of closed interval can be also considered. The behavior near the boundary is also studied, but it's more complicated. So I just mentioned this simple case. So graph of xi in A0 is the following type. So 1, but except find countably many points. This is 1, and otherwise this is some interval. Right. And moreover, we have a compactness. We have FV is actually in some sense coercivity, we assume, but if this energy, singular modica Mortora energy is bounded, then there's some sequence which combines to some xi, which belongs to A0. So something like that. So this is quite good. So if you believe this theorem, if you use this theorem, we can easily explain what we obtain in our earlier picture, earlier graph. So if f prime v is positive for v is greater than 1 and negative for v less than 1, then g's must be convex. So this 2gp plus p square is strictly convex. In this case, when minimizer is unique and fv v minus 1 square, if fv is more explicit, so that v is this one, then we have such functional, and this is it is minimizer is just p01 plus b minus 1, and the minimal value is exactly what we found in our example. So, what is the singular limit of Kobayashi, Warren, Carter stuff? And as we expected, we have the singular limit of this type of singular modica Mortora type, but we have also the energy type. So energy is if the case V tends 1, this is equal to 1, but there's some jump discontinuity related to u plus and u minus and xi minus. If xi minus plus is there, then we have such kind of part. So this comes from a total variation part. But you see there's some weight remains at the jump discontinuity. Ju is not a jump discontinuity. Okay. And u plus and u minus denote the trace u from each side. The topology is L1 in L1 in U, and the graph convergence in V. So U is missing here. And higher dimensional case, what is a suitable topology? The graph convergence is not appropriate. We introduce new notion of the convergence, so that slicing argument works. This slicing argument introduced by Fonseca and Liu, 2017. So this slice is just if you have a set value function and the gamma x is compact in R, the value is compact in R, and we take the slice. This is just a notation. Omega 1x is the time interval, t interval in the direction of this one. So I should say this one is if for fixed x, okay, fixed x, because the omega x nu, this is in some sense slice. And if you're interested just one dimensional interval, we understand this one dimensional interval. And gamma x nu is just a value here of gamma, and pi nu is a projection in the direction of nu. So we are given new direction and x, and then we can slice. So this direction, including x. And okay, what is the topology? The reason I mentioned here is that we have to introduce some topology. And topology is a little bit complicated from the higher dimensional case. These countable dense, so the graph convergence in higher dimensional set turn to be not so good. So we consider another topology. These are just countable dense set in Sn-1. So this is the set of direction. BD is the set that the set of set value function that gamma is measurable as a set value function, and nu for each direction in x omega nu, this gamma x nu is the closure is the same as gamma x, so in some sense compacted, and graph x nu is compact, and B is a union of this kind of set, this kind of family of set. And topology is for one-dimensional case, we have a graph, household distance graph, and for each given nu, we slice, and in each slice, we consider such kind of function. And this is in the direction of slice, and this is a parameter of slicing. So we consider such kind of distance. And for countable dense set, D, we consider the distance. So the direction set, and this is the usual way to consider the graph, consider distance for such kind of that's kind of family. And the sliced graph convergence is if gamma m combines gamma and the sliced graph topology, if for some countable set, it's dense, such that gamma m and gamma PD and the distance, the d gamma m to d gamma combines to 0. So this is for some d, so it's kind of an inductive limit of some topology. So it's a little bit complicated. For technical reason, we restrict Xi as the special shape, one outside Xi and Xi minus Xi plus on sigma. And then Xi minus locally in L1 as the sigma is assumed to be countably N minus 1 rectifiable set, and Xi minus Xi plus locally in L1 as a function of sigma, as a function on sigma. And moreover, Xi minus is this interval always contains 1. Then we have gamma convergence. It's not exactly gamma convergence, but assume that V epsilon tends to Xi in the sliced graph sense. Then we have lower semi-continuity, and for any Xi, there is V epsilon, such that V epsilon combines to Xi in the sense of sliced graph sense, and the limit is actually attained. Limit energy is actually attained. So I think I have a few minutes. So I just mentioned a few words about the idea of the proof. For higher dimensional case, we don't give a proof today. And the idea is reduction to one-dimensional problem by slicing. And the one-dimensional case can be proved by unfolding, which is introduced in our paper. The higher dimensional result is still weak compared with one-dimensional case, because we do not have a good compactness. So sketch of the proof for one-dimensional case. Okay. U is, okay, we introduce such kind of arc length parameter of graph curve, y of ux. So this is the arc length parameter of the graph. On the graph, yes. Yeah, and x is a horizontal axis, yes. And the inverse functions, of course, always Lipschitz, and the Lipschitz. So this we can consider inverse function, and always Lipschitz continuous. Oh, this is S of x. If you consider C1, it's fine, but if it's not okay, if it's not, if it's yes, the function itself may have may not be a continuous function if U is not C1, but we would like to consider this S in the VV for U in VV. Okay. So we define the unfolding U by arc length parameter of the form U of S and U XS. So in some sense, curve would like to be this way, right? But we would like to unfold so that this still have some angle. So the basic property is if U is W11, so derivative absolutely continuous, then U is Lipschitz, and Lipschitz U this unfolding is always Lipschitz continuous. And luckily speaking, this total variation U and total variation U, big U is the same. This is trivial because US is by definition. This is UX, U sub X, so that's a derivative, 1 plus UX square root. So this is the US is less than 1. This is trivial. And TV U is, of course, US, but if you change the variable, you get again the same. So this is what we observe, right? That we consider this problem in the interval I0R, right? So this is a total variation. It's a total variation of big U and little u is the same. So if U epsilon is a bounded total variation and bounded, then big U epsilon tends to be subsequently converges. And the Lipschitz V is less than 1, and total variation V is, of course, below or equal to lim inf TV U epsilon. So this is something lower semi-continuity. And the value of V is maybe time is almost up. U epsilon tends to V when U epsilon takes lemma 10. Assume that U exception. So this is inverse function of length parameter. Then this is a relaxed sup limit is a maximum value of V, and the x bar x is x. So this is in some sense Lipschitz continuous, but can be flat part. So may not be can be flat part. So there we have a V exist, and we can have these two things. And then we can estimate total variation. And if limit sup is still positive, there's at most countable x, such that this x bar has the value of xi has a multi-valued x bar value the value the place where x bar equals xi is an interval, non-trivial interval. Let Xi denotes such a set, and we decompose jxi by sub-intervals, and we can write it in this way. So U epsilon is like this, and V is something like that. The Lipschitz constant is always 1, actually. And we can estimate below from this using the maximum value of V carefully. And I don't explain, but we can estimate TV from below in this way. And okay, if there's boundary, then we have if there's there's no intersection with boundary, it is simply 1. It's chi. And rho xj is actually maximum value. So you see this kind of maximum value we take. So we consider, so the proof is, I think I have 2 more minutes. Ideal proof is for limit inequality is forget about boundary effect. So first, like usual Modica-Mortora inequality, we have this one, and then remove soup inequality, then applying theorem 10 with U epsilon and GV epsilon to get such kind of things, but TV is dominated by this quantity, and this quantity is actually, we can calculate gxc minus plus or gxc minus plus for 2 of j's. Right? We thus obtain such kind of estimate. And here V epsilon combines xc was assumed. If there's a boundary point, the results are more involved. So we can estimate by using such kind of maximum value of V by G. So and we apply this to get Kobayashi-Warren-Carter, limit Kobayashi-Warren-Carter energy, which I would like to skip. Higher dimensional case is very involved, so it's better to skip all stuff. And then I conclude part 1 by saying a couple of open problems. There are many open problems. What kind of compactness do we have? Does a minimizer exist for 0 Kobayashi-Warren-Carter energy for given F? If one-dimensional case, the answer is actually yes, but higher dimensional case, we don't know. And we minimize in Xi we get with sigma 1. So if you minimize this energy, Xi already, then we get such kind of total variation, Kobayashi-Warren-Carter type total variation energy, right? With this one. So what's the difference? Usually, if you talk about this JU, it's jump discontinuity. If you talk about usual total variation, there's no divisor here, only numerator here. But here we have such kind of divisor, and this is of course not convex in the variables. So this the minimizer of this energy is not so clear because this is not convex. And what is the natural class of Xi in higher dimensional case is not so clear. So I think I left many problems, but just to mention typical one. So I think this is the end of my the talk of my first part. So let's go back to my theory. Yeah, for example, this one, but it's better to even one-dimensional case. Yes. Okay, thank you very much, and let's stop. I'll stop part 1. Thank you very much for listening.
So let's try if the question works. So if there are some questions, can you hear us, Yoshikatsu?
Yes, I can hear you.
Okay, perfect. So please, if there are some questions, be addressed. Goro has one.
Okay. So in one-dimensional case, the bounded variational function can be somehow turned to be modified to be continuous function by taking arc length parameter or something like that. But the higher dimensional case, I cannot imagine how to somehow modify setting to be continuous functions. So is there any trick to change variables or in a higher dimensional setting?
Thank you for your interesting questions. Let's see. Yes, I skip completely higher dimensional case. So that's the natural questions. Okay, the idea is to reduce the problem to one-dimensional case. Okay, so this is the idea.
Okay.
Higher dimensional case, we sigma disjoint union of countably many compact set in C1 hypersurface. This is a countable rectifiability. And we consider this set is almost flat, right? And then each such kind of discontinuity, we take nu1 and nu2. Yeah. So, and we observe this is we slice. So no, this is a coordinate change, and we slice. So this is a main issue. So we slice. Yes. So this is a disintegration, right? Or Fubini theory, right? And slice, and then we reduce the one-dimensional case here. And using one-dimensional result, we get such kind of property. So I hope I answer something, at least for infinite.
I see. So by slicing, in a sense, the problem is reduced into one-dimensional case on each slice. But finally, you have to integrate everything by each slice.
Yes.
Okay,
this is quite involved. Yeah, I'm sorry. This is quite involved. So, yes.
Okay, thank you very much.
Other questions? Marks? If not, let's thank the speaker again.
Thank you very much.
Assume it like more or less 5 minutes for the second part of the lecture. Just another technical announcement. For the lunch, there is some people who didn't choose the second dish. So please do it or
not do it.
Or not do it, but you have to pay anyway. There is no restriction. I mean, the menu
There's
is
no hub menu.
there is no off menu. So if you want to do it, please do it right now. That we have to bring it to the rest. So I wait.
When did you?
At 45, like 2 minutes to resume.
Okay.
2 minutes.
We resume in 2 minutes, right? Okay.
Hello, Jotgatu.
So
How is life in Japan? Regards from Spain.
Luis, come here. You have to come to the.
This is microphone.
Hello, I wanted to say hello to you. Do you see me? I think so. I'm looking at the blackboard. Okay. Anyway,
So
I will listen to your second talk.
yes, thank you. But I have a problem to share the screen right now.
Okay.
Escape, just escape. But escape key cannot work.
Okay. Konnichiwa.
Konnichiwa. I don't know how to escape. Huh?
スクリーンは今来てますけど、
Okay.
I have a problem.
もし共有してるんだったら上の方に緑色と赤い色がのバーがあって赤い方をクリックすると消える。
Yes, I understand, but I have a problem because everything is. How do we escape? Yeah, I can only see my slide only.
Okay, just a moment.
Just a second, sorry. But ずれますか。一回消すかないか。I quickly escape and then I come back. Sorry.
Okay, yes. Okay.
Sorry, I now come back. Just a second.
Yes.
Do you see my do you listen my voice?
Yes, I can see and I can hear.
Okay, then I'll share the screen.
Yes, please.
Oh. I will share the screen. Just a second. Is it visible now?
Yes, perfect.
So this is would like to be full screen. Okay, sorry.
Perfect.
Let me continue second part. I lost a couple minutes, but I hope now it's visible. Okay, second part is the joint work with Kuroda. Other than Okamoto, Sakakibara, and Uesaka, there are two people join, Kubo and Kuroda. Kubo is actually a master student of Hokkaido University checking calculations. Okay. Here's a problem. First, I explain problem. And I should apologize. This is a completely linear theory now. So the title of symposium is a nonlinear diffusion. So this is has a problem maybe. But what is interesting, we get some time fractional time differential equation as a limit of Kobayashi-Warren-Kata system. Okay, so what is the Kobayashi-Warren-Kata energy? As I explained before, this is the same I explained before, so I just skip it. But this can be interpreted as a gradient flow. We consider now gradient flow of this energy. So the inner product is something weighted inner product, and yeah, this is if we consider some weighted inner product, then you get such kind of gradient system. As I mentioned before, Kobayashi-Warren-Kata energy is convex for each variable, but not convex as a combined variable functions. So this is gradient flow. And so, okay, this is if you change the scale, then you get the Kobayashi-Warren-Kata. And the year is 2000, sorry, not 2020. And the depending variable is the meaning of dependent variable, as I explained briefly in my part 1 talk, is with order parameter, and with 1 is ordered, but with not is one is it's not close to 1 is amorphous, and U is the average angle of each grain. This is the idea of Kobayashi-Warren-Kata energy. And the single limit problem is the following: consider single case. And this is f of v is something like very simple and just square, and alpha v is just v square, and then you get such kind of equation explicitly. And we are interested in what kind of singular limit as epsilon tends to 0. And we are now studying this problem, but today I can only give you the very partial result of this question. So we just consider this trivialization of the second equation. And we consider UV as UV is a jump, it's a kind of Heaviside rank function, and it's 0 for X negative part, and B the positive part, and B is positive. So this is just a Heaviside function, B times Heaviside function. And if V takes its minimum at X is equal to 0, then UB, this above one, is actually standing solution of this alpha V of UT, this equation. So time independent solution with the Dirichlet condition. This one. But the meaning of solution actually should be rigorously interpreted because of this divisor. So if you, so we have to give a rigorous meaning of this equation. But today I'd like to skip it. So anyhow, this is some particular solution of this, some special solution of this. It's a first, second total variation type equation. So we forget this U equation and then consider just the V equation. V is the order parameter equation for order parameter. Yes, this is the equation. And we are interested in what's the limit as epsilon tends to 0. And it turns out reasonable scaling is this tau 1 over epsilon. This tau 1 is positive. This is reasonable scaling to get structure of this problem. In the Allen-Kahn type equation, so this is a double well type, the equation looks similar, but correct scaling, reasonable scaling to produce a mean, to produce a mean coverage of flow is tau is equal to epsilon tau star. So this scaling is different, should be different. This is anyhow horizontal variation. This is vertical variation. So this is different, I should say. I don't know the much better explanation, but anyhow, this scaling, correct scaling is different. So we consider this tau is equal to tau 1 over epsilon. It's positive constant tau 1. Then it's a completely linear problem. Oh, by the way, this is a derivative of the Heaviside function. So this is actually delta function. And consider this type of equation. So we just put this constant tau 1 over epsilon and this type of equation. And then yes, and the Neumann boundary condition. And what is the limit problem we as epsilon tends to 0? Okay, and if x is equal to 0, we expect v tends to 1 because epsilon tends to 0, so v are forced to be 1. How, or almost everywhere. How about the behavior of the value 0 at the value 0? And this is a linear problem. So we eventually get fractional time differential equations. So we said tau 1 is equal to 1 to simplify the notation. Our equation can be written as the gradient flow of modified singular modica molecular energy, right? So this is the L2 gradient flow. It is okay. And what is the limit? We know by part 1 that this modified singular modica molecular epsilon singular modica molecular combines to limit singular modica molecular with this one. And this is if we just jump this quantity just 1 point, just it's a very simple form, b xi square and 2g zeta. And this in particular example, this is a c minus 1 square. So this is a energy. So we know the energy comprises. So it is expected that this limit x energy is so we are interested, of course, the limit of the jump this the singular part. Okay, v epsilon is expected to be very singular at 0, and we are interested in the limit of v epsilon over x 0t. And xi epsilon is okay. We set this value as xi epsilon, so we are interested in the limit of xi epsilon. Of course, naive guess is there should be a gradient flow of this limit energy. This is a naive guess, but it turns out this is wrong. So at least for well-prepared data, that means if there's a constant, it's 1, and this is a if v0 epsilon is combines to 1 outside, x is equal to 0, and the near x is equal to 0, we have such kind of behavior, so exponential behavior. Then this is I'm sorry, this is A, I think, well prepared case. There's a misprint here. I'm very sorry. This is A. And okay, and assume V epsilon is a solution of V, and with Neumann boundary condition with initial data, assume that V0 epsilon well prepared. So then the V epsilon combines the set valued function 1 and in the household distance graph, and it's combines the closed interval x0 and t. So this is a convergence, something like that. And well preparedness in the previous slide, sorry, this is not C, this is A, is not important for this statement. So we have the convergence. And we have the characterization of limit equation. This is the most interesting part of this problem. And Xi must solve this type of gradient flow, but this is a kind of fractional derivative in time. So what is the actual form is Xi0 is of course 1 minus C because of our assumption, but MAT is just okay. This is F alpha beta is especially power type and also exponential type, and gamma Euler gamma beta divided by Euler gamma beta, and if we can write this MA is explicitly in this way. It actually turned to be positive and actually decreasing in time. If A is equal to 0, the left side is equal to F01 half. And this is nothing but Caputo half derivative dt xi. And of course, if with epsilon is not well prepared, we have another equation, another term exists. The row of the term, but another term exists. And this is a convolution, and this is not theta. This is 0. Sorry for many misprint. Consider the boundary solution of heat case. Okay, I am talking about some related problem. And consider the boundary solution of the heat equation on the half interval with the Robin boundary condition. Assume that initial data is constant with some C. And then the boundary value of C of W actually solves the Caputo derivative, half Caputo derivative big C. So formally, Wx derivative, so this is a negative part, so this is exterior derivative, actually. And this exterior derivative looks like, of course, half derivative, or half, okay, half of second derivative. So this should be a half of Wt. So this is formally it's reasonable, right? And it's actually Caputo derivative. We can prove such kind of things. So for this is completely linear, but if we take a trace, we get such kind of result. And the very famous paper by Caffarelli and Silvestro saying that Laplacian minus Laplacian alpha is obtained at the Dirichlet-Neumann map of degenerate Laplacian. And of course, we are able to assert similar things. Consider this type of degenerate heat equation in the direction of x. And 0t is this center value is eta, boundary value is eta, and eta 0 is 0. And assume that W is vanishing at tends 0 at x negative infinity. And the initial data is 0. Why? Then we obtain that the first the derivative we obtain this the derivative of so if you the derivative x is actually dt gamma eta c gamma. So c gamma is some constant, and we found all exponent, right? So this is the first derivative of the boundary one is can be understood as the time derivative of eta, fractional time derivative of eta. And here's the derivation. And this is just mimic the Caffarelli-Silvestro approach. And we consider such kind of fundamental function which tends to 0 and 0 values 1. And just take Laplace transform to get this one. And then we get by scaling, we have such kind of W. And thus we end up with such kind of things. And since eta 0 is 0, we get eta lambda is equal to eta t hat Laplace transform over lambda. So in other words, Wx derivative, exterior derivative of W is equal to psi prime 0 and f 0, convolution of f 0 1 minus gamma convolved by eta t derivative. Note that if gamma is less than 1, this guarantees the integrability of f0 1 minus gamma. We know psi prime 0 exists and positive by Caffarelli and Silvestro. Okay, so this is a proof of such kind of statement. So exterior derivative can be calculated by the fractional time derivative. So we are going back to the original problem and the characterization of the limit. we consider E cross equals E times epsilon. Then you get such kind of equation for x less than L. But if you rescale and delete this type of type stuff, we end up with a big V equation. But domain is now L over epsilon. So this is still linear equation, but domain is moving. So the limit equation formally is the following. We get such kind of equation. So this is a big V, I think. For well prepared initial data, the limit of initial value is in the scale is this guy, right? So now epsilon is disappear by rescaling. So we have such simple problem. And boundary value, still, I'm sorry, this V is big V. The boundary value problem, okay, if V is even in Y, then V is, of course, even, so V1 is equivalent to the boundary value problem. Our question is to derive the equation for Xi, this values. So we shall show V1 and V2, for example, using Laplace transform, and everything can be very explicit. We consider W as just V minus 1, write X instead of Y. And the V1 is of the form, this equation, and V2 is of the form for W equation. This is a completely linear equation, and it turned out it's a very nice exercise for the Laplace transform. Yes, this is our goal is to prove such kind of equation. And therefore, if you if you write W language, this should be the eta ds, and it is eta plus 1. So the remaining thing is mostly calculation, and we consider Laplace transform, and we just transform Laplace. We make Laplace transform for W equation to get such kind of equation. So this is a Laplace transform time variable, and we know the time derivative of the Laplace transform of time derivative is equal to lambda W hat and W0, and of course, if the Laplace transform 1 is lambda minus 1. So we are interested in W hat, which is bounded in X. The solution of it is of this form, because of this is a constant coefficient of second order differential equation. So everything is explicit. And A is constant to be determined. And we determine A so that delta part of Wxx second derivative equal to delta. This inequality, right? This should be delta part should agree with this delta part. So we differentiate, and the delta part of W hat xx second derivative this guy, and now we get this type of equation. This is W hat 0 lambda is A minus. So we already calculate A here. And we thus obtain the hat is this one. And actually everything is computable eventually. And I think this hat should be bigger hat, I think. Okay. So we are calculate this eta. And we have eta hat, the Laplace transform of eta is equal to this one. So we calculate, we multiply and subtract eta t to get this kind of equation, and we can write it. And then right hand side is already the gradient of energy. And so what's the left hand side? And the left hand side is, if you know the many formula of Laplace, we can prove this is a Laplace image of MA. Thus, we get such kind of things. So this is an idea. But this is just a calculation. Interesting calculation. And if you consider the general initial data, then we have, there's a couple of term remains. For example, this term remains and this term remains. And the GA is this is a green function of this second order ODE. And the G lambda, this is a convolution X and the W0, and the GA is such kind of things. So if it's inverse Laplace transform, this is formula for eta equation. And if your initial data is not well prepared, but still exponential and with positive mu, so if mu is equal to A, it's well prepared. But if this is not well prepared, then we can calculate this guy by using error function. Error function is something like that. And note that this actually, if you use error function, you can write it in this way for MA actually. So if mu is equal to A, then this is MA eta 0, and MAT times eta 0 is exactly equal to this term, and this term, two term vanishes. So this is a story of the in this special case. And in this case, we can calculate the eta of t explicitly, actually. Yeah, eta of t is this formula, and eta t is okay. Q mu is such kind of things. Actually, this is very related to MA. Deleted just exponential part. So this is a Q mu, and if you use QB, eta tilde, eta bar is just this quantity, and we can write it in this explicit form. And we often use this Laplace transform Q mu is just root square 1 over square root of lambda plus mu. In particular, Q mu is positive. Actually Q mu is positive because MA is non-negative. So Q mu is actually positive and is integrable, since this guy is actually the value 0 is actually 1 over mu. So this is a positive function, an integrable function, and we have explicit formula of AT in this way. Then we have okay. What I would like to say is this eta bar is important term. Eta bar is very important term, and its limit is exactly what we are interested in. B plus A. This is actually a stationary point of S0 SMM, and eta E is an error term. Actually, eta E is exponential decay, and we can have such kind of estimate. Okay, and we just give a brief proof. If no, this is full proof. Sorry. If QB is positive, the limit eta equals, okay, you just have a integral infinite. Why this may be just infinite. So you take infinite. So this is actually minus maybe some constant. Yeah, so this is too much, we say. So this is, if you calculate this guy, then this must be a 1 over A plus B. So limit eta is B minus B times this quantity. So maybe we have to divide by minus B to make this sentence correct. And since 0 infinity, so this guy is always mu plus B, 1 over mu plus B. And we can be calculated in this way. And fortunately, so we include this one, this part here, then you get this, but still this is less than 1, and QB is integral. So this integral tends to 0 as t tends to infinity. And this is so even if you multiply e a square t, this is negligible. So this eta bar tends to be b plus a, yeah. Okay. And our convergence theorem follows from convergence relation in a rescaled variable, and V epsilon be a solution of this one, and with initial data V epsilon, and let V be a bounded solution of this equation. And convergence lemma is if initial data converges with 0, in the sense that this may be L, I think. In this sense, then V epsilon converges with locally uniformly, in particular, Ct converges to Xi, not V epsilon, locally uniformly in 0 infinity. Sorry, there are many typos. So what it looks that locally uniform convergence will follow by maximal principle. However, the domain of definition different. So the proof is a little bit involved, even if V is equal to 0. We decompose two cases depending on whether V is odd or even in X. We only give an idea of odd case since it is simpler. If V0 epsilon is odd in X, we need not consider delta term. We compare this equation to this first system to the second system. So epsilon system to the non-epsilon system, limit system. Looks very similar, but domain is different. And this is a Neumann condition is assumed. For the limit equation, we assume boundedness, for example. We extend V0 epsilon to even function with respect to L over epsilon and extend it periodically. But note that V0 epsilon bar for this periodic extension may not be close to V0. So we only compared in L infinity, but not in the whole L infinity R norm. We approximate with initial data. And for this initial, by maximal principle, we can compare we can control V epsilon, V delta epsilon solution in this interval. This is by maximal principle epsilon problem. And Ascoli Arcera says that this is a subsequently converges to the limit equation, and this is by uniqueness. This is a solution of a limit equation with modified rho delta. And we then compare, so the uniqueness of limit guarantees the convergence, actually full convergence. We then compare the V delta, V epsilon, and V delta and V, which is easy to handle by the maximal principle. We can compare V epsilon and V epsilon delta, and V delta and V maximal principle for epsilon equation and delta equation. And then it's fine. So we prove the convergence in the V delta level, so modified level, and then yeah. Otherwise, we cannot estimate this one, right? So modified level, we use such kind of maximum principle, and then the modification is okay. Is the last in the by Ascoli-Arcera type argument. Okay, so the limit equation. What is the limit equation of Kobayashi-Warren-Carter? I hope I have a few more minutes. Kobayashi-Warren-Carter system is a problem, as I mentioned before. And what is the singular limit equation for this problem? Is a problem, and this is the weighted total variation flow, and this is regarded by the weighted total variation flow with respect to weighted L2 norm if V is given, if V is independent of time. And the equation can be interpreted as this way. And Z is a kind of Kahn-Hoffman vector field, but this is a much more explicit way to write equation. And Z is a Z the du, so this is the z gradient u, is equal to the total variation, weighted total variation. And actually, this the du is what is called uncertainty pair, which is formally equal to the z dot gradient u. Here, with your square gradient square is a measure so that u belongs to the weighted B function with weight v square. Of course, the field Z is called the Kahn-Hoffman vector field. And this interpretation, for example, found in the book of Andrew Bayo, Caceres, and Matson, at least for both are constant case. So one-dimensional piecewise constant case we would like to consider. U is consider U. This is the angle variable. It's a piecewise constant function. And there is a periodic boundary condition to simplify the issue. And P is, so this is U is a picture. The graph of U is like here. And chi is actually sign. If it's a jump, this is positive. This is a negative jump. This is minus. This is chi 1. Assume that there are no new jump. Then we formally get such kind of equation. And Cp is because of this condition, we get Cp is just chi I, chi j, with j is equal to 0, 1, m minus 1. So this is what we obtain. And chi j is the signature of hj plus minus hj. So, okay, this is this kind of problem is already studied by Miho Giga and myself and Kobayashi long time ago. But if we postulate that each facet stays as a facet, then we have if you integrate it, then this hj is it can be calculated by integrated. By integrated from one interval, you get such kind of estimate. If we epsilon tends 1, outside Pj, we have such kind of equation. We get Cj is some the limit of V. Yeah. So the jump with Bj is hj plus 1 minus hj at Pj. The equation V is a little bit cheating because Bj is now time independent, but still we have such kind of equation. And this equation coupled with such kind of equation. So this is and the local existence of solution is rather standard if you use such kind of fractional time derivatives ODE theory. But we have to be a little bit careful because in Bj, one has to, this Bj may be 0 somewhere. So this is almost the end of my talk, and then further problem. Okay, my derivation of the limit Kobayashi Warren Carter system is in some sense formal, except U is a standing solution. Time independent solution. So we'd like to justify derivation even one dimension. Is there any chance that new jump will form for you during evolution? This is important because if V is identical equal to 1, no new jump for the total variation flow is formed. This is studied by these people, Bonforte and Figari, one dimension. But in nowadays, there's a lot of such kind of studies by, for example, Michał Wasita and Piotr Lipuka, Shambor, and many people study such kind of problem for when the V is equal to 1. But if you consider A of x, A prime has a jump, then monotone function U0 form a jump because the solution must be Ta prime x plus U0. So because of this one, if A has jump, the solution may construct another jump because of this. Okay, let me summarize. We rigorously derive a singular limit equation for one-dimensional Kobayashi-Warren Carter equation when the angular variable has a jump at one point and does not move as T develops. The limit equation not conventional gradient flow, it is a fractional gradient flow. we formally derive the singular limit of the original one-dimensional Kobayashi-Warren-Kata system. Okay, thank you for listening. Sorry, I'm a little bit over the time because of travel, but I hope you enjoy my lecture. Thank you very much.
Well, are there some questions? Marks?
So I'd like to discuss about the convergence of solution for time fractional gradient flow to some equilibrium. So you mentioned in the middle of your talk.
Which one? This one?
Yes. So then the final solution converges to a stationary point. So the critical point of the functional, right?
Yeah, exactly.
Yes. So in this concrete example, can you also prove the decrease of the energy along the orbit of solution one?
So, sorry, I understand. Okay, this is a very concrete, right? What is the question?
Yes. My question is, in a standard gradient flow, the energy will decrease in time, but in a fractional case, it seems a bit unclear. So how about it's not this concrete case?
It's not so clear. We did not check it, but yeah, that's a good question. This should be decreased, but I don't know. We did not check it in this aspect. That's interesting.
Actually, some people working in numerics try to reveal this question, and some people say there might be numerically counterexample, and some people say it should hold. It's important question in this field, I would say. Thank you very much.
I think so. One thing I can say is if you go back to original Kobayashi-Warren-Kata system, the energy is always decreasing, right? And for the energy level, it's this is a limit of the Kobayashi-Warren-Kata type energy. So I think in this particular problem, this energy should decrease. That's my impression.
Okay, thank you very much.
So, are there other questions?
Yeah.
Luis?
Thank you very much, Gatsman. I want to know, in connection with this gradient flow, that the energy should be decreasing, if there is any control of the energy dissipation. The derivatives for the energy in time should be something that can be controlled. Is it possible?
Okay, I just say I did not check it, but this is the energy comes from Kobayashi-Warren-Kata type. So and the Kobayashi, we know the dissipation of Kobayashi-Warren-Kata type energy. So if the limit is commutable, then we can say some dissipation rate. That I can answer right now.
Okay.
Yeah. So
it's something that can be. This is something that can be further investigated to control how this energy dissipation allows the problem to converge.
This is a very nice point, I think. Thank you very much for your suggestions. We just finished this part, so there are so many problems left. So yeah, but this is one important point. Yeah, thank you very much.
Thank you.
Are there some other questions? If this is not the case, thanks Yoshikatsu again.
Thank you very much for your listening. Yeah.
Thank you very much for being here with us, even if remote. So let me say that now we can all go to lunch, and we resume this afternoon at 3. And it will be again on Zoom and on YouTube transmitted. So see you later. Bye-bye. And see you in, well, maybe later for you it's too late, but maybe tomorrow you want to reconnect and see you.
I may attend. Yeah.
Bye bye.
Thank you very much. Thank you very much. Bye. Yeah.
伊賀先生、ありがとうございます。
どうもありがとうございます。
He says no control.